Hi, this video is going to focus on how we figure out which of the discrete distributions is an appropriate model for different situations. I did make this flowchart, which is available on Blackboard, to help you think about which distribution would be an appropriate model. You will not be provided the flowchart on exams, but I think it is a useful tool to start learning what questions to ask yourself when you're trying to decide which of the distributions is an appropriate model. So first thing that I always like to think about when I'm trying to figure out which discrete distribution might be an appropriate model is thinking about whether there are independent trials, repeated, in which there are just two possible outcomes for each trial, and the probability of success stays the same for each trial. If that's the case, then I next ask myself if the number of trials is fixed. If the number of trials is fixed, then I tend to think about, okay, well, number of trials is fixed, then I'm going to generally be working with a binomial distribution, and the random variable x will be the number of successes that occur in that fixed number of trials. If the number of trials is not fixed, then usually what I'll be interested in is how many trials are required in order for something to happen, right? And generally it's how many trials are required to have a particular number of successes. If the number of successes if I'm interested in is 1, right? So I just want to know how many times do I have to do this until the first time that I have a success. Then k would be equal to 1, and I'd have a geometric distribution. If I have a situation where k is not equal to 1, I'm interested in a number of successes that's more than 1. How many times do I need to flip a coin until I have 3 heads, right? Now k is equal to 3. Then I would use a negative binomial distribution. Now if I'm not in a situation where I'm looking at a random variable, that is the number of trials needed to have a certain number of successes, then none of our distributions fit that situation. So we would not be working with any of those distributions. Now from the beginning, if I did not have a situation where I have independent trials with 2 possible outcomes and the same probability of success in each outcome, then I'd have to start asking myself different questions. Say, okay, is x the number of times that a particular event occurs over some interval of time or region of space? If the answer to that question is yes, then it may be appropriate to use a Poisson distribution. Remember that there are some assumptions that occur with the Poisson distribution. For instance, that events occur independently of each other, and the probability of an event occurring in 2 events occurring in a really short interval of time is very small. A number of other assumptions for the Poisson process, so you need to think about those, but the Poisson is often a good choice in that situation. If I'm not looking at the number of times that an event occurs in an interval, then I will think about whether or not I have 2 kinds of objects that I'm interested in, and would be selecting a particular fixed number of them without replacement. If I'm selecting them without replacement and I'm interested in the number of items of one of those types, I can use a hypergeometric distribution. If I have a situation where I don't have 2 types, the only other sort of distribution we might have is a discrete uniform distribution for one of our special distributions, and that would occur when I have a fixed number of possible outcomes, all of which are equally likely. For instance, when I roll a die and I'm looking at the numbers that might land facing up, and each one is equally likely. So that would be the other possible special distribution of the discrete ones that we have. And if we have a situation that doesn't fit any of these, then again, we would have none of our special distributions would be appropriate for modeling that situation. So I'm going to do a couple of quick examples related to sampling balls from an urn. If we have an urn with 30 balls in it, 15 of the balls are blue, 10 of the balls are red, and 5 of the balls are white. There are a lot of different random variables we could define in this distribution, and we could choose some that have different distributions. For example, if I let x equal the number of balls selected from the urn with replacement, until a white ball is taken. This is a situation where I have repeated independent trials, taking one ball out of the urn and putting it back. Because I'm putting it back, the chance of the next ball being white remains the same, regardless of which ball was chosen before. So I have 2 possible outcomes, which would be white or not white. And I have the same probability of success for every time I make a choice. Is the number of trials fixed? I want to know how many balls need to be selected. Each selection would be a trial. So here the number of trials is not fixed. Is x the trial number of the kth success? How many balls are selected? Yes, this is, right? Until I have one white one. And k is equal to 1. So this would be a situation where I would have a geometric distribution. The geometric distribution is parameterized with p, the probability of success on each trial. And since there are 5 out of 30 balls that are white, that would be my p. Now if I chose a different random variable, suppose now I take y, and y is equal to the number of red balls selected if I pick 5 balls with replacement from the urn. Now again, because I'm selecting with replacement, I do have repeated independent trials, each having 2 possible outcomes. Now I'm thinking of my outcomes as being red or not red, and the same probability of being red each time. Is the number of trials fixed? Now I know I'm picking 5 balls, so I have fixed number of trials n equals 5. And so my x is going to be the number of successes, the number of red balls out of that fixed number. So I have a binomial distribution. Sorry, y has a binomial distribution. Binomial distribution, I need to know n is equal to 5, and I need to know p, the probability of success for each trial. Since I'm interested in the probability of getting a red ball for each selection, there are 10 red balls out of 30, so that would be my p in this situation. Let's consider another random variable. R is going to be the number of blue balls selected if 5 balls are taken from the urn without replacement. Now, because the balls aren't replaced after they're taken out, if I pull out a blue ball the first time, the chance that the next ball will be blue is going to be, instead of being, there were 10 blue balls, no, 15 blue balls. So instead of being 15 out of 30, it would be 14 out of 29 the next time. So because that probability is changing, I don't have a situation where I've got independent trials with the same probability of success. X, the number of occurrences in of an event in a continuous interval or region. No, this isn't looking over a continuous region of time or space. This is looking at a fixed number of discrete trials. So this is not that situation. Is the event selecting at random from a set with two types of items? So although really there are three different colors of balls, I'm really only interested in two characteristics, right? Whether they're blue or not blue, so I can consider this way, right? And X be the number of items of one type. Yeah, X is the number of blue ones out of a fixed number of balls chosen. So the answer to this question is yes here, and I have a hypergeometric distribution. In this case, for the hypergeometric distribution, I need to specify a number of things. I need to specify little n, which is the number of balls selected. That's 5. I need to specify n1, which is the number of blue balls in the urn. The number of blue balls is 15. I need to specify n2, which is the number of not blue balls, also 15. N, my total number of balls in the urn, is n1 plus n2 is equal to 30. And so if I wanted to find the probability that r is equal to a particular value, little r, I'd use my hypergeometric distribution. On the bottom, I have the total number of ways I could choose 5 from 30 objects. On the top, I have the number of ways I could choose r of the blue balls and 5 minus r of the 15 not blue balls. And that would be my probability mass function for this distribution. And keep in mind that r could take values from 0 up to 5, because I can't choose fewer than 0 blue balls, and I also, since I'm only choosing a total of 5 balls, can't choose more than 5. And we'll do one more random variable. This time I'm going to have z be equal to the number of balls selected without replacement before all 5 white balls have been removed. Now, just as with the last scenario, because we're selecting without replacement, I don't have independent trials with the same probability of success. I also am not looking at the number of occurrences of an event over a particular continuous interval of time or space, so I can't use a Poisson. My random variable x isn't the number of items of one type, it's the number of total balls that need to be taken out. So I can't use the hypergeometric distribution. The outcomes that are possible, think about it, I would have to choose at least 5 balls in order to have all 5 white ones. And I could choose anywhere, if the last ball I pulled out happened to be white, then I could also have up to 30 balls that I needed to remove for this to happen. So this would be my support of Z. And all of these are not equally likely, which means I don't have a discrete uniform distribution. And so I'm in a situation where none of our special distributions could be used to model that situation. So I hope that this gives you a little help working with the flowchart and just thinking about how to identify what we're looking for. Keep in mind that for a binomial and the hypergeometric, both have a fixed sample size n. What's different is that the binomial p is constant, for each trial. Hypergeometric, the probability that you'll choose an item of a particular type changes because of sampling without replacement. The geometric and the negative binomial distribution neither of them have a fixed sample size n. The random variable x will be equal to the number of trials required to have a particular number of successes. The geometric is a special case when k is equal to 1. The negative binomial is more general. K could be equal to any integer. And both of these require that p is constant for each trial. I hope this helps as you're reviewing these distributions and thinking about when you can appropriately model with each of them. Thanks. Have a good day.